All right, class. Welcome to this week's video. We're going to be talking about normal distributions and z-scores this week. I think this week's content is going to feel like a step up in what we're trying to do and what we're looking at here. I think we're making a huge conceptual leap, so it's very important that you understand the particulars of the things that are going on here. So the first thing we want to look at is exactly what is the normal distribution. We've been talking about it and referencing it for a little bit. And we really need to have a clean understanding of like what it is and what we can do with it. So first off, right, it's a bell-shaped distribution. It's symmetrical on both sides. And it has this characteristic where it follows this behavior that for example, approximately 68% of the values are within one standard deviation from the mean, okay? So we've seen this. There are a lot of different types of distributions that are normal in shape. So that's one of the reasons why we use them as often as we do. Looking at this distribution I have as normal. This one happens to be centered at 0. But not all normal distributions will be, right? When you take data, the average of your data probably isn't going to be 0, so your data will be at, the mean will be somewhere, and you'll have this bell-shaped symmetrical distribution around wherever your average is. But just to kind of look at this, and to point out a few different things. So here's where the average would be, right here in the middle. The mean, median, and the mode are going to be in the exact same place for a normal distribution. And then I have down here the standard deviations marked out, right? Here's 1, 2, 3 standard deviations, and then the same thing on the other side, but just negative, okay? So what that one comment was saying up there, the 68%, is that if I look between -1 and +1 standard deviations from the mean, right? So in either direction, I'm within one standard deviation of the mean. This represents 68% of all of my total data, right? It's going to fall within one standard deviation of the mean. We can bump that up if we look instead at 2 standard deviations from the mean. So now I'm going from here out to here, right? All of these individual data points, right? This would be like a frequency distribution. This is going to represent now 95% of my data, right? 95% of the data that I'm dealing with will be within 2 standard deviations of the mean. And then really the last step we need to take then is, if I go out here, between 3 standard deviations, okay? If I'm within 3 standard deviations, 99, these are approximations, but approximately 99.7% of all of my data is going to be within 3 standard deviations if we're looking at a normal distribution, okay? So that's one of the really cool things about normal distributions is if you know what the standard deviation is, tells you a lot about where your data is and what exactly it looks like. So there's a special type of normal distribution called, I'll get to that in a second. So one of the things we can do with normal distributions is there's this thing called the sampling distributions of means. And I'm bringing this up now as a sneak peek. We're going to talk a lot about the sampling distributions of means in a couple of weeks. That's going to be really important to us. But there may be a time where you're collecting data or you're looking at a set of data and it's just not normal. The shape of the distribution, you may have a frequency distribution and your shape may be something like crazy looking, right? Not normal at all. And so none of the really cool things that apply to normal distributions will apply to the distribution you're looking at, right? If this is the thing that you're dealing with, this isn't normal at all, right? We want a shape that looks something like this. But if the graph, the data that we're dealing with is the blue graph, well, that's not normal, and we can't use it. So oftentimes what researchers will do is they'll use this idea called the sampling distributions of means. And really quickly, the way that this works is they say, okay, let's pretend that this bubble here represents my population. And we know that, let's just say that we know that the distribution of this population is this crazy looking thing, definitely not normal. And so what can we do about this, right? So what they do is they say, all right, I'm going to go into my population, this circle here, and I'm going to take a sample. So I'm going to randomly sample the people in here and pull them out. So here's my red sample. And I'm going to sample it again. I'm going to go through and I'm going to randomly sample again, and I'm going to pull all those out, and there's my blue sample. And I'm going to go in and sample again. And I'm going to sample, and I'll get a yellow sample, and then maybe I'll get an orange sample, right? Realistically, for the sampling distributions of means, pretend that you did this an infinite number of times, okay? So I've got all these little samples of the population, okay? And for every one of these samples, I'm going to calculate an average. So here's a mean, here's a mean, here's a mean, here's a mean, right? Okay, actually, if these are the averages of samples, they should be X bars. X bar 1, X bar 2, X bar 3, X bar 4. So I've got all of these averages. And then what we're going to do is we take all of these little averages and we make a distribution of the averages. Okay, so this is the frequency of the averages. And this distribution, oh, that was too pointy, will be normal every time, okay? The sampling distribution of means, or the distribution of all of the samples of the population, or the means of all of the samples of the populations, will always be normal. And so we can do some really crazy things with this. And we'll talk about that in a couple of weeks. But just a sneak peek that if you're dealing with data that is not normal, often we can use the idea of the sampling distribution of means to then have a normal distribution to kind of work with. Okay? And we'll look more closely at the sampling distributions of means later. But just to give you a sneak peek and an example of a distribution that will be perfectly normal every time is the sampling distribution of means. Did we talk about the standard normal? Oh, I skipped that one. Here we go. Okay, so there's the normal distribution, and the normal distribution, it might be centered on 0, but most are not, right? It could, you may have taken a sample and you may have gotten a normal distribution, but its mean, its average is out here at, I don't know, 10 or some other value, whatever, but it's not centered on 0. The standard normal distribution, it's a regular normal distribution that has an average of 0 and a standard deviation and a variance of 1. And we use this in statistics because I can take my weird distribution and then look back to the standard normal distribution to say some really cool things and to make different hypotheses. Okay, but that's the thing, is that if they're talking about the standard normal distribution, you know the mean is going to be 0, and you know the standard deviation will be 1 every single time. Okay, so what we need to think about is, well, why does this matter? Why have this thing? And the whole reason goes back to looking at these standard deviations. So I have each of these places here. Here where the standard deviation is 0, 1, 2, and 3, and then the negatives. And the really cool thing about these distributions is we can say, okay, look, between between -3 and -2 standard deviations, 2% of your population or your sample or whatever the data it is that you're looking at will be within 2 to 3 standard deviations. Between 2 and -1, this percentage is 14%. And these are approximations, right? They're really decimals, but I'm approximating them, okay? And then between 1 and 0, like I already said, there's 34% of your sample in here, okay? But if we look between 3 and 0 and add this up, so I've got 16, and then the 34 brings me to 50%, which is good, right? Because out here at 0, right, if that's the mean, the median, and the mode, then 50% of my sample had better be to the left. Now again, these are all approximations with decimals. Really, if I look beyond -3, so because this curve technically keeps going, and there is a little bit of space in there, there's approximately 0.1% of your data will have a standard deviation larger than -3. And then these percentages are the same over here, right? This is also 34%, this is also 14%, this is also 2%. And then out here in this region, beyond is, approximately 0.1% of your data is going to will have a value with a standard deviation of greater than 3. And what this allows us to do is to say some really cool things about the data we're looking at and about the different values and ranges. So let me give you an example. So let's say this, okay? Let's say you want to know what is the range. So let's say we have a bunch of data of newborn infants, okay? And you want to know what is the range of birth weights that make up 90% of all newborn infants in the United States. So I looked up a couple of statistics before we started, and I found that, and I forget what year this is for, but about the average birth weight is 7.5 pounds with a standard deviation of 1.8 pounds, okay? So here I've got a standard normal curve, okay, because it is centered on 0, so this would really be 7.5 in the data, not 0. And then one standard deviation would be 7.5 plus 1.8, right? That's one standard deviation. Anyways, what the question is asking us about is it wants to know, okay, well, what is the exact range that for 90% of newborn infants, right? What does that range look like? Well, I can use the standard normal to figure that out, okay? And we can start by looking at the standard deviation. So if I go from -1 to 1 standard deviation, I know that this covers, from before, that's about 68% of my population, right? So 68% of all newborns, their weights will fall within 1 standard deviation, okay? But that's not good enough, right? The thing wants 90. If I pop out here to 2, and if I go between the 2's, that's 95%. So this is going to be too much. So I need to know exactly what 90% is going to be. And so the way that this works is you'll see, you can look these tables up online, or there's one in the back of the textbook. But here's your standard normal, right, centered on 0. And we'll look at Z-scores here in just a second. But the way that these tables work is they say, we're out to some z, okay, or to some standard, I'm just going to call it for now a standard deviation. I'm out to some standard deviation, and I want to know what percent of my population, that's what this shaded area is, what percent of the population falls, from way out here up to where z is, okay? And so, for example, if I wanted to look at a z-score of minus 1.6, or a standard deviation of negative 1.6, so that would put us right about here. Then, well, there's my negative 1.6. And if I wanted greater decimal accuracy, right, we can look here. So this is negative 1.60. And that tells me that this area from out here up to here is going to make up this value right here, or 0.0548, which is 5.48% of the data is going to be out here in this range. Okay, that's kind of what it's showing here. Now, we want to know 90%. I know that between here and here is 95%. So we know that we're going to be somewhere in here and somewhere in here, right? So let's just draw this out and say, okay, this is going to represent 90%. And so I need to cut off this back part. Well, how much is left? What's over here and what's over here? If the middle is 90, that's going to leave 10% left. So this has to be 5%, and this has to be 5%. Okay? So essentially what I'm looking for is what is the standard deviation going to be when I have 5% of my data trapped out here in this area. So now I can come over here and look. Here's 5.3%, 5.2, 5.1, 5.05, and 0.49. So my 5% lives in this space right here. So what value is that? Well, it's negative 1.6. And then I go over, up 4. And then see, it's not quite, it's 4 or 5, it's not quite 2.5 yet. So I'm just going to give it an extra half, so it's negative 1.645, because it's not 1.65, but it's also not 1.64. It's in between, so negative 1.645 is going to get us in between. So that tells me that if I want to know where 90% of the data is going to be, I need to look at values between negative 1.645 standard deviations and then out here to positive 1.645 standard deviations. So we're almost there. I know the range of standard deviations now. So to finish this, I just need to go a little bit further with the data that we're looking at, okay? But to do that, we need to know about z-scores. So let's take a look. So a z-score is it's the number of standard deviations above or below the mean any given number in your data set is. So just to run a couple of really quick examples, this is the data from last week's video. So looking at hours of sleep, we calculated last week that for this little sample of hours of sleep, the average ended up being 8 with a standard deviation of 5.477 hours. So I have both of my statistics for the z-score, right? Except for this mu here stands for a population average, and the sigma is a population standard deviation. We really just have a sample average and a sample standard deviation, which is just S. So I could replace those with, you could say this is X minus X bar over S to calculate Z. But those are just logistics. Anyways, so let's just look at a couple of these just to kind of get a feel for what a z-score is. All it's really doing is telling us is I can look at my data and I could say, let's pick two random values. Let's pick 4 and 18. And let's find out what is the z-score of each of these values from my data. So to do that, so for 4, its z-score is just going to be 4 minus 8, right? Because that's the average divided by the standard deviation, 5.477. Now notice above, this is going to give me a negative number. This ends up coming out to be negative 0.73. Okay, and then if I go over to my standard normal, right, here's where the average is, and so this is technically where 8 would be sitting, and with the standard deviation of negative 0.73, that puts me right about here, right? Right about there for that point. Okay. So I'm within the one standard deviation rule, right? So essentially this tells us that the 4 for 4 hours of sleep falls within that value, the 68% of all parts of my data. Okay, well, let's look at 18 and see what 18 comes out to be. Well, so for the z-score for 18, I'm going to take 18 minus 8, and notice that's going to give me a positive number this time, divided by 5.477, gives me a z-score of 1.82 when you run that through your calculator. Okay, so that puts us out here at almost 2. And again, we can kind of think about what this means is if I'm almost to 2 out here, that means that this score, number one, it falls within 95% of my data because that's for the 2 mark. But it's also, I mean, if this thing was 2, if we approximated it to be 2 standard deviations, so if we made it 2, that means, so here's 50%, and then in this section I have 34%, and then in this section I have 14%. So if I add this up, that gets me to 83 or 84, and add 14 more takes me to 98, right? That means that this 18 hours is in the 98th percentile, you could say, right? It's 98% of all the other scores are lower, are less, right, than the 18. Meaning that 98% of people from this population get less sleep than 18 hours of sleep. If this data really, I just made these numbers up, but if your study had those values, that's what it would be telling you. So the z-score really can tell you a lot of cool things. The other thing that I really like about the z-score is if you look at the units here, this would be, in our example of hours of sleep, this isn't hours of sleep, this isn't hours of sleep, this isn't hours of sleep. The units divide out, so you're left with this number with no units. It's a unitless number. It's a normalized number. So I can take this and I can make comparisons between studies. So let's say that this 7 hours of sleep represents somebody named Jimmy. Actually, let's pick one that I actually know the z-score for. Let's say that this 4 hours of sleep represents Jimmy. And so I know that this is a z-score of, what did we calculate that out to be? Negative 0.73. Well, let's say that I have other data on Jimmy as well. Let's say I have Jimmy's history score and his science score, like test scores. And so let's say that in history Jimmy gets 80% and in science Jimmy gets 75%. The cool thing about Z-scores is, number one, these percentages don't really tell me very much. What if the average test score in history class is a 95%? That would make Jimmy below average. But what if the average test score in a science class is 50%? That would make this 75% above average. Okay, meaning that this thing would have a positive z-score, a larger positive z-score, but this thing would have a negative z-score. So directly comparing the 80 to the 75%, you can't do that. But you can compare the z-scores, and then you can tell something. You can look at the z-score and say, oh, Jimmy's actually kind of good at science, and he's okay at history. He's just barely below average in history, but he's quite a bit above average in science. But if you look at the percentages alone don't tell that same story. That's the really cool thing about z-scores. And then you can also look at Jimmy's, so this is comparing test scores directly, but then I could also come back and compare it to his hours of sleep. You can look here and you can say, oh, he's below average, right? The negative z-score tells you that it's below. He's below average on the amount of sleep that he's getting. Not that much below, right? He's still within the main body of data, right? Most people are getting about the same amount of sleep that Jimmy gets, but he's a little bit below average. And so z-scores allow you to really talk about what's going on within the data that you have. So they're really great. One last thing. Let's finish this example from before, okay? So returning to the birth weight thing. We calculated, we found from the table these standard deviations, right? We know that the standard deviations of birth weights that make up 90% of infants range from negative 1.645 to positive 1.645, but what values do those correlate to, right? Telling someone what the range of z-scores is or what the standard deviation range is isn't very helpful, right? These are z-scores because they show like how how many standard deviations away from the mean is a given value. So I can take this and using my equation, right? So the z-score equation is the value minus the average divided by the standard deviation. I can just plug this stuff in. I can say, okay, negative 1.645 is equal to x, the thing that I want to know, right? The actual point in the sample, minus the average, which for us we're saying is 7.5, or the data that I found said was 7.5, divided by the standard deviation, which is 1.8. When you run these numbers through a calculator, so multiply each side by 1.8 and then add the 7.5 over. So your lower bound over here, this correlates to a weight of 4.539 pounds. And then when you do this exact same thing, you're going to put this in here, but it's just going to be positive instead of negative. This upper range correlates to 10.46 pounds. So what our data is showing is that 90% of newborn infants have a weight somewhere between 4.5 pounds to 10.5 pounds on average. And we can find all of this stuff out just by knowing the average of the sample and the standard deviation, and using these ideas of z-scores and the standard normal curve to think about our data. So, a couple last things. This video is a little bit longer than the other ones, but But like I said, this material is a little bit more dense. One last thing I wanted to look at is kind of thinking about this in terms of probabilities, okay? This curve that we're looking at, so here's our standard normal curve, right? And I can find a z-score of something, so this one is here. And let's just say, let's imagine that this z-score happens to be negative 0.75. Okay. What that would tell you is, now looking here, I can't find that on this table because it's not an option in these ranges, but let's just say that I knew that this, if I know that this is a negative 0.75, you could look up in the table and find out that, in fact, this is going to be 22% of the data, and this larger section would end up being 78% of the data. Because in either case, this and this, they have to add up to 100. Okay? Because these are probabilities. What this is saying is that if I know that this is a z-score of negative 0.75, I know that 22% of the data is lower than that, and 78% of the data will be higher than that. And if I want to know what the difference is between my z-score, like, well, what's the probability then of being in here between the z-score and the mean? Okay, well, if on my curve, if this is 22%, and I know that the mean is always at 50%, okay, well, how much more do I need to get? This has got to be, the probability of being in between there and the mean is going to be 28%. Because, right, 22 plus 28 is going to get me to the 50. Let's do one more example, but let's use the table this time. So this time using the table, oops. This time using the table, let's say that I've got, let's find 25% on here. Okay, so if you're looking, these numbers are all too small, right? My biggest number here, that's not even a percent. And we would know that because that's out beyond 3, right? These numbers are kind of useless. But down here, so if I find 25%, it's right here. Shoot. 0.0, oh, hold up, that's not 25%. That is, hold up, just let me change colors here. This is 2.5%, because you move the decimal place twice. So this value here correlates to 2.5% of my population or my sample. So if I want to know what z-score is going to have is going to be greater than only 2.5% of my population, I look at the row that I'm in, so it's going to be, so out here, this is going to be negative 1.9, and then I can add a 6. Okay, that's going to mean that out here on this little tail, I have 2.5% of the population below this z-score of negative 1.96, and then out here, this is going to be 97.5% of the population larger than this z-score. Okay? Because these two things have to add together to bring me back to 100. So that's a little bit about how probability works into this. There's a lot going on in this week's material, and it's critical that we all have a really good understanding of what the normal distribution is and how z-scores operate within it. Take some time, really think about what's in the problem set this week. If you have any questions, send me emails. I'm happy to coach anybody through any more of this as you're working on this stuff. Have a great week, and I'll talk to you next week.